Okay. Now let's run through some of the more likely questions you'll see that have to do with electrophilic aromatic substitution reactions. So first off, one of the most common ones you're going to run into is the one that involves the Friedel-Crafts alkylation reaction. So let's put 3 carbons there, a chlorine here, and we're going to react that with a benzene ring, and then AlCl3. So go ahead and pause the video if you want to try this on your own, otherwise let's get started. So first things first, what does AlCl3 do when you have a carbon chain with a chlorine on it? Well, the electrons of the carbon-chlorine bond go to the aluminum and you get AlCl4 minus, plus you get the carbon chain without the chlorine. Now because the electrons from the carbon-chlorine bond went to the aluminum, this chlorine took its electrons and went, this carbon lost a bond and becomes positive. This is the carbon, the positive carbon is where the benzene is going to add. But is it going to add to this carbon? Remember, whenever you do this reaction, you get a carbocation, you have to think back to Ortho 1 and that principle that carbocations are unstable and like to move to more stable positions if they can. That said, what will happen is a hydride shift. But wait, there are no hydrogens available on this carbon here. So what will happen? A methyl shift. You only do methyl shifts if there are no hydrogens available to move. So in this case, one of these 3 methyls will switch positions with the positive. All 3 methyls are equivalent, so it doesn't matter which one you choose. And now I will have the positive here, and that methyl has shifted. Let's make that blue. That methyl right there. Now the benzene will react with this. Okay, so now the benzene's coming in. And if you have trouble visualizing where that benzene should connect, well, what you can do is just draw in your benzene. And since there are no groups on this benzene telling me where things are going to be added, all of these carbons being equivalent, I can just draw a connection from this carbon to where that positive is, and erase the positive, and I know that this will be what my final product looks like. But now let's go through the mechanism of this to see how it looks, or how we get there. So, back to this. We have this positive charge right here. And we know that is going to interact with our benzene. So I'm going to erase this, give myself a little more room. We have our benzene. Now, the only thing in benzene that has electrons that can go out and do reactions and make bonds are the double bonds within that benzene. So one of those 3 benzene double bonds are going to go out and give its electrons to that positive carbon. Okay? And so we end up getting actually, since I want to make it that carbon, let's say I started my arrow from this double bond, just so it's consistent. Okay, benzene. Now, when you do this reaction, number your carbons so you can keep track of them. Let's say this carbon that I'm attaching to is carbon 1, and then this carbon over here is where that carbon is attaching to, carbon 2, 3, 4, 5, 6, 7. And remember, these numbers don't have to be in order. All they are markers to keep track of where things end up getting connected. So we say carbon 1 was the benzene, carbon 2 is where I added, carbon 7 and 6 were attached to 2 as methyls. So let's say this is 6 and this is 7. And then I also have 3, which had 5 and 4 on it. So coming off of 2, I will also have, let's say it goes this way, 3 and 4. So 3, 4, and 5. Okay? So this would be my major product of the reaction. The most common mistake students will make is after that chlorine comes off, or rather before we even consider where that chlorine comes off, we just say, well, this is the spot where that chlorine was, that's where the benzene is going to attach. And so people will choose this as the major product, where the chlorine was here, and you got that. But remember, whenever you do a Friedel-Crafts alkylation reaction, the reaction that doesn't involve the double bond O, you will always do a carbocation, you will always form that carbocation, and it will shift with either a methyl or a hydride if it can move to a more stable position. Okay? So this would be the wrong answer. Wrong. this would be the correct answer. Okay. Another common question you're going to get that deals with benzene additions is which ring is most reactive, or which benzene is most reactive? And to explain that question, well, let's come up with one first. I'm going to give you 3 benzene rings. Okay. On one benzene ring, I am going to put a nitrogen, a double bond O attached to that nitrogen, and then some CH3. On this carbon, I will put a chlorine. And now on this one, I'm going to make it look mostly like what that first structure looked like, but I'm going to switch the order. Now I have double bond O, N, and then a CH3 and a hydrogen on that nitrogen. Okay? And all 3 of these reactions are going to react with Br2 in FeBr3, a reaction that just adds a bromine to the ring. The question being, of these 3, let's say this is 1, 2, 3, who is most reactive and who is least reactive? Well, the first thing to do is to look at the groups that are attached to the ring. We have an amide, a nitrogen single bonded to a double bond O. We have a chlorine, and then we have another amide, but in this case, the double bond O carbon is the one that's closer. If you go to your cover sheet, you're going to see a list of things that are listed as activators and deactivators. Now, some terminology. Activator is synonymous with electron donating group. And as the name implies, it makes the ring more reactive. And the stronger the activator, the more reactive, the more reactive the ring will be. Deactivators are the opposite. Deactivators are synonymous with electron withdrawing groups and make the ring less reactive. The stronger the deactivator, the less reactive the ring. So now let's look at these 3 structures. What you want to do is focus on the thing that is single bonded away from your benzene and cover up everything else. So if I look at this going to the nitrogen, I'm going to cover up this because that is not single bonded to the benzene. The nitrogen is. And if you look at your cover sheet, you will see that nitrogen is a strong activator or a strong donated group. Activator. Okay? If you look at your cover sheet again, chlorine is listed as a weak deactivator. And if you look at your cover sheet again, cover up everything that isn't a single bond off the benzene. So just that double bond O carbon. If we thought about the resonance structure of this, we know that the electrons swing up towards that oxygen because oxygen is more electronegative than carbon, meaning this oxygen would be O minus, carbon positive. If you have something that's positive, a single bond away from your benzene, you're pulling electrons towards that carbon. So whenever you see C double bond O, that's a single bond off the benzene, think of it as a withdrawing group or a deactivator. On your cover sheet, C double bond O is typically written as CHO or COR. If you see that, actually no, not COR, it's, actually yes, COR. Okay, COR corresponding to a ketone, CHO corresponding to an aldehyde, where it's a hydrogen instead of a methyl. Okay, now, so I know that if I look at my cover sheet, a C double bond O is listed as a moderate deactivator. Okay, so now I have a strong activator, something that makes my ring super reactive. This is by far going to be the most reactive. And now I have a weak deactivator and a moderate deactivator. Since this is better at deactivating, it's making your ring less reactive. So this will be the least reactive because it is the most deactivated. And so this would be in the middle. So in order of increasing reactivity, 1 is the best, 2 is in the middle, and 3 is the least reactive. Okay? All right. Another common question you will get has to do with where groups will be added. And again, if you look at your cover sheet, you're going to have things listed as ortho para directors and meta directors. So let's touch on that real quick. What does ortho mean? What does para mean? And what does meta mean? So I'm going to draw a 6-member benzene once again. And let's add some groups on. All right, so at the very top, I'm going to put an OH, and I'm going to base things off of that. So let's look at this carbon that the OH is attached to. If I draw a methyl coming off of there, CH3 right there. These groups, I look at the carbon they're attached to on the benzene. So carbon 1 here, and then 1 over the CH3. So this is the 1-2 position. These are 1-2 apart. We call the 1-2 position the ortho position. If I add a Cl over here, now I am 1, 2, 3 apart, and we call that position the meta position. Finally, let's say I add a bromine here. This is 1, 2, 3, 4 away, so we call this the 1, 4 position, the para position. Okay? And now, if I remember, this can be used to describe any group's relationship to another group. So if I look at this chlorine, I can say it is ortho to the bromine because it is 1, 2 away from the bromine, and I can also say it's ortho to the CH3, 1, 2. Okay? Now, why does this matter? Why do we need to know what's ortho and para? Because of the way things add to benzene. So if I start with the benzene and I do a simple reaction like Br2 FeBr3, you're going to add a bromine to the benzene. And since all of these carbons are equivalent, there is nothing on any of them that makes them different from the others. That bromine can be added arbitrarily to any of these carbons. I'm going to choose the top, but you only add one bromine. Now there is something on the ring. So if I add another thing to the ring, it matters. Meaning, if I choose to use the reaction HNO3 and H2SO4, what this does is it adds an NO2 group. But where it gets added depends on what's on the ring. I have a bromine, and if I look at my cover sheet, I am told that bromine is an ortho-para director, which means I have two possible products I can make. I can have one where the bromine directs the NO2 group to the ortho position, and I have one where the bromine directs the NO2 to the para position. Okay. Which one is preferred? Which one will be your major product of the two if we're telling you there's only one major product? Well, here I have electrons on that bromine, I have electrons on these oxygens and nitrogens, and they're going to kind of repel each other. Or you could have two really large carbon chains in those ortho positions, and they're going to bump into each other. So the ortho position is always going to be a little less stable than the para position in terms of stability. And this is only comparing ortho to para, because if you have a meta director, it only directs meta. With that said, if you have both the ortho and the para positions available, add to the para position first. Okay? So this would be our major product, but if we were asked what the two major products are, we would put both the ortho and the para position products. So if I were to do a question based around this, let's now change the order of events. Let's do another one. First I'll do HNO3, H2SO4, followed by FeCl3, Cl2. And I've been writing Cl2 on top of the arrow, FeCl3 on the bottom, but honestly it doesn't matter because they're both being mixed in at the same time. So let's do step one. HNO3, H2SO4, what does that add? That adds an NO2 group. And again, since there's nothing on the benzene, I can put this wherever I want. I'm going to put it here this time, NO2. Now, NO2 is a very strong withdrawing group. And if you look at your cover sheet, NO2 is a meta director, meaning it directs to the 1, 2, 3 position, 1, 2, 3 position. So both of these are meta to the NO2. So when I do that Cl2 FeCl3 reaction, the chlorine will be added either here or here. Now both are the same because there's a plane of symmetry here, so it doesn't matter which side I choose. But this would be my major product. NO2, and then a Cl here, or if I chose the other side, that's just as acceptable. Okay, so now let's go through a synthesis problem. If they're going to keep the synthesis simple on the exam, you're only going to have to add 2 things to the benzene. But we're doing retrosynthesis, right? So let's put a carbon chain here, and let's put a Cl here. Okay? So now we have to figure out the order of events. The first thing to do in any synthesis question that involves additions to benzene is to relate the positions of your groups. We see that this chlorine is 1, 2, 3 away from your carbon chain, which means these are in the meta position to each other. Now we check our cover sheet and see, well, how do these groups direct? We know that chlorine, based on our cover sheet, is an ortho para director. So here, here, and here. So it can't direct this carbon chain to where we want it to go. Also, if we look at our cover sheet, any carbon chain is also an ortho para director, meaning it will direct here, here, or here. Again, not where the chlorine ended up. So what do we do? Well, there's a nice reaction we have. Remember what zinc, mercury, and HCl does? What that does is it takes a carbon chain that has a double bond oxygen on it, that was a single bond away from the benzene, and erases that double bond O. And so what you go back to is this, with the double bond O. And like we mentioned earlier, C double bond O is a withdrawing group, and for that reason, it is a meta-director. So the really important point to make is the use of zinc-mercury reduction allows you to choose whether you want to add ortho or para starting from a carbon chain. If you want it to be added to the para position, you use zinc-mercury. Or if you want it to be added into the para position, you add the group first and then add the zinc-mercury. In this case, we do the zinc-mercury first because we need to get that chlorine in the meta position. Okay? So now, how does this work? Now I have an ortho-para director and I have a meta director. So I have 2 options. Do I add the chlorine first or do I add the carbon chain first? Well, we need the carbon chain to be on the benzene ring when we add the chlorine. So it can be directed meta, which means I need my reactant to look like this. Because this is a meta director. When that chlorine comes in, it will be added to the meta position here or here. Once that chlorine is added, now I just have to add this group, and the way we add that is our AlCl3 with our carbon chain. So I'm cutting this bond off here, so all I'm going to do is redraw this whole thing here over the arrow. And then the carbon that has the double bond O, you put a chlorine on that as well. And there we go, we're back to benzene. Okay, so these synthesis questions will always make you stick things onto benzene or take things off, but you'll never have to synthesize benzene itself. We're never going to teach you how to do that, and from what I hear, it's a nightmare, so don't bother. It's not worth the time. Okay, so this is how you approach a synthesis. Let's do one more synthesis like this, though. I'm going to give you mostly the same structure, but now I am going to change the position of the chlorine. I'm going to put the chlorine here, okay? And this one will turn out to be a lot simpler than the last one. Okay, so again, I'm going to think about the positions of my groups relative to each other. I have a chlorine here, 1, 2, 3, 4 away from my carbon chain. So they are in the para positions. And we know that both chlorine and carbon chains are para directors. So it actually turns out it doesn't matter which one I choose to put on first because both will direct the other group in the right position. But let's add the chlorine first. Now, I don't want to use zinc mercury as my first step because then I turn it into a meta director. Okay? And for the record, I wrote FeBr3. I could write AlCl3 or AlBr3 or FeCl3. What matters is the halogen 2. If I want to add chlorine, I need this, but all of these do the same thing. They pull the chlorines apart. So the other chlorine left over can do the reaction. Okay, so technically your cover sheet has this one, FeCl3, so I'll just try and stay consistent with your cover sheet, FeCl3. Okay, so I'm adding the chlorine in my first step. So now I go back to this, okay? And now I just need to add the carbon chain. Now, on your cover sheet, you have two reactions that add carbon chains. You have the alkylation reaction. See, I have 1, 2, 3, AlCl3. And I have the acylation reaction, the one where it's the double bond, it's not a double bond O, chlorine, and then the carbon chain I'm adding, AlCl3. Now I cannot stress this enough. We have already seen a practice question where we saw this does carbocation shifts. And this is why I'm stressing this point. This reaction right here is the one you should use for synthesis only. This reaction, because it can do carbocation shifts, may end up giving you something you don't want. For example, if I tried to do this reaction to a benzene, the product I would actually get would be that. Because I'd get a carbocation on this carbon, which would shift to the secondary carbon here, and then this carbon would attach to the benzene, that carbon being this, okay? This reaction, on the other hand, never runs into any issues. There are no technicalities, no special rules. You just say, this is the carbon with the chlorine on it, that's the carbon that gets added to the benzene. But we do have to do one extra step, because this adds a carbon with a double bond O on it. I don't have my double bond O yet. So I can't do this right off the bat. I need to do one more step first. And that is zinc mercury to get that double bond O in the position it needs to be. So react with that benzene, get your double bond O back on the chain there, and now you can do the reaction that adds the carbons. So I'm breaking this bond right here, so redraw everything exactly the same. Put a chlorine there, and AlCl3, bringing me back to my benzene that I started with. Okay? So again, I can't stress this enough. Stick to using this reaction here when you want to add carbon chains. Yes, you have to add in one more step if you don't have that double bond O at the end, but one, you don't have to run into any carbocation shift issues, and two, as we saw in the last question, having this double bond O can sometimes allow us to choose whether we want to direct meta or para. If I wanted to direct para, I wouldn't have used this step until I added the chlorine, like we did in the previous synthesis. Here, though, I want the chlorine in the para position, so I did it before I added the chlorine. I got rid of that double bond O, so my carbon chain became a para director again. Okay? And with that, those are most of the synthesis problems you're going to run into on your exam.